Okay, so we'll continue on from where we left off last class period. I just set this over here before I forget my demonstration because, well, we'll see. Okay, so remember this showed up as the last slide last class period. The key to this is talking about the difference between mass and force or weight. Weight is a force. Remember I talked about a force is anything that pushes or pulls. Mass, what is mass a measurement of? What? Yeah, mass is a measurement of how much matter is present. So how much matter is going to weigh something. And so there's a relationship between how much matter is present and how much something weighs. And that relationship is really simple. The force of gravity which we also think of as our weight, is simply equal to the mass of the object multiplied by a constant g. And this g we call the acceleration of gravity. Why is it called the acceleration of gravity? Because that is the rate at which the velocity will change if I drop something and gravity is making it fall. And so our textbook is making the approximation here that g is approximately equal to 10. What are the units of acceleration? Meters per second squared. Now, more accurately, g is 9.8 meters per second squared. And it depends on where you are on Earth, how much it might differ from that. I use San Francisco as my reference. At San Francisco, it's like pretty much exactly 9.8000. If you go somewhere like Denver, you're a little farther away from the center of the Earth, and it goes down a very small amount. If you go somewhere that's close to the center of the Earth, it'll go up a little. Something you may not know. The Earth is not a perfect sphere. We're not a perfect ball. The Earth is spinning. What would happen if you took a sphere of nice soft clay and went to the pottery class and put it on that turning wheel and spun that wheel? What would happen to the clay? It would flatten out. And that's what the Earth does because it also spins. And so the equator is out there where it's spinning the fastest, and so it fattened out. So the equator is farther from the center than the poles. So if you go to the equator, it's going to be farther from the center and you have a slightly smaller g. If you go to the poles, you're actually closer to the center of the Earth and you have a slightly bigger g. And so we can just take the force of gravity is the weight, and it's the mass of the object times g. The standard unit for mass is the kilogram. So if I take a 1 kilogram mass and multiply it by g, which our textbook says is approximately 10 to make the math easy, 1 kilogram times 1 meter per second squared, 10 meters per second squared, have that written down here. I have force of gravity is equal to mg is equal to 1 kilogram multiplied by 10 meters per second squared. And of course, everyone here can do 1 times 10 in their head, right? Yes, thank you. So that's 10. And our units are kilograms times meters per second squared. So that's a unit of force, a kilogram times a meter per second squared. But that's a lot to say. And so we define a new symbol that is the Newton. And 1 Newton is equal to 1 kilogram times a meter per second squared. Now notice I put a lowercase n when I put the unit Newton. If we talk about Sir Isaac Newton, for whom it is named, then we put a capital N, right, for his name, proper noun. And the symbol is actually with a capital N. How fun is that to remember what has to be capitalized and what isn't? You don't have to remember that. I'm not going to test you on that. Please don't put for your potential test question today. Brandon's all, what the capitalization rules are. Everybody should have one, right? Because you took 2 yesterday. And I'll print more for class on. When's our next meeting? Wednesday, that's right. And of course, it's supposed to have a snow and ice storm between now and then. So, batten down the hatches. Okay. So I'll have new ones for you next week. So that's how we calculate weight. So now everybody knows this, but we can put meaning to things. You know that I weigh more than Brandon, right? Why do I weigh more than Brandon?
This is an awkward question.
It's awkward. There's more of me, right? I am a bigger gentleman. And because there's more of me, that means my mass is bigger because mass is a measurement of how much matter is present. And then the weight is the force that matter makes because of the gravitational attraction of the Earth. And so because I have more mass and we have the same acceleration of gravity, then I'm going to have more weight. Sorry for the awkward question. Yes, Casey.
So that's why you're the same amount of mass here and in space, but your weight is different?
That's correct.
Gravitational difference?
That's right. And that's the way to make sure students know there's a difference between mass and weight, because the mass doesn't matter where you are. It's good that you mentioned that because that's our clicker question coming up. The weight that matters where you are. I don't know why I left this in here. We already talked about density. I already saw, somebody had for their potential test question, which has higher density, blah, blah, blah. Answer was gold. So the clicker question we just referred to. The density, it's the density instead of the weight or the mass. Let me go back one slide. What is density? It's the mass per volume. It's talking about how much mass you have in a fixed volume. So the density of 1 kilogram of iron, the mass per volume is what?
Sorry, what was the session idea?
Okay, the session idea is, and I'll write them here. Actually.
Isn't it web first?
Yes. And the fizz is all capitalized, although I don't think that matters. Or it's channel 33.
And if we paid for the thing, if we just use our clicker, is it supposed to work?
Uh-huh.
Okay.
As long as you register your clicker with the thing you paid. Even if you don't have it done now, you can always do it later. You can answer, it'll record your answer, and then you can tie it together later. You'll be pleased to know I'm not going to count yesterday's because, frankly, I screwed it up. I combined yours with the next classes, but it gives you, some learning area, just like I have some learning area here.
Does it show something for me?
It shows Stacy, Eric, Haley, Skyla, Carmen, Casey, Valerie, Brandon, Jackie, Vanessa, Candace, Larissa, 8CA592, Hannah,
That's me.
and Tiffany.
What do I have to do so that doesn't show my code?
I have to update it.
Okay,
I didn't update before class.
all right.
That's me. Okay, that's 15 out of the 17. I will move forward here because we've got to get going. We had 3 people that said less than the moon and 12 that said the same on the moon. Now, I tried to make it clear here that density, does anybody know what the symbol is for density? It's actually a Greek R. I know it looks like a P, but the Greek P is pi. This is rho.
It doesn't make sense.
An ancient Greek. Okay, so if density is mass over volume, then certainly Larissa could tell us what the correct answer is, right, Larissa?
Yeah. Right. Well, isn't it just what Casey just talked about? Like, because density is different than weight, so that's gonna presume constant.
Okay, the density is the mass over volume, and the mass is going to remain unchanged. And if it's iron, the iron isn't going to expand or shrink because of being on the moon. And so the volume stays the same. And hence, the mass divided by the volume stays the same.
You're welcome, guys.
Yeah. All right. Now to talking about forces, because we're going to talk about equilibrium. And before we talk about equilibrium, we have to talk about forces. Forces, I said, were anything that pushes or pulls. You might remember my example where I did not touch her. But I said that if I were to push on Brittany, why, that would be a force that I'd be putting on her. And she would be putting force on me that's exactly the same. When we talk about forces, we usually draw arrows to indicate the forces acting on an object. So here we have on the left an object that has two forces acting on it. We might say that's like a car, and Casey and I are each on one side of the car pushing on the car. Well, the combined force of Casey and me, since we're both pushing with 5 newtons, is 10 newtons, because you just add them up. Now, there's direction to those forces, though. What if Casey got in the front and I got in the back and we're both pushing toward the center? Kind of like a tug of war, but in reverse.
Why would we do that?
Well, we want to see who's stronger. And if we're both pushing with 5 newtons, but in opposite directions, what's that going to add up to?
0.
0, right. Which tells us there's really not a point in doing that unless we just are doing a test of strength to see who can get more, force. And then here's the more realistic one. I'm putting 10 newtons on my side, and Casey's putting 5 newtons on her side. When we add those together, because mine is 5 more and they're in opposite directions, we get 5. Now this brings up, how do we add vectors? Force is a vector. What reason can you give me why force has to be a vector?
It has to be like in a direction.
Has to have a direction, and vectors have directions. Right? I can't push on something in all directions. I push on it in one direction. So force is a vector, and if I'm going to add vectors, we do it the way my teachers taught me to add, like in first grade. There was none of this Common Core stuff. And by the way, you guys are all having to learn this, right, in education classes? As I try to analyze it, what they're doing in Common Core is trying to teach you what I consider the tricks to make it easier. And that's good and useful. What I think is a flaw is they don't spend as much time working on the fundamentals and go straight to the tricks. So Elette was working on her math lesson the other day, and she had a number that was like, they were supposed to calculate 143 minus 59. And I said, well, the way I actually do this is the Common Core way. I say 143 is 3 more than 140, and 59 is 1 less than 60, and 140 minus 60 is going to be 80, and then I have to take the 3 and the 1 into account, and I get 84. That's essentially the way you do it with Common Core, right? But first I had to understand what's going on when I'm adding and subtracting before that makes sense to me. So, as you're teaching, think about how it's going to make sense to the students. If you think that going straight to that is going to be the fastest and the best, that's your thought. But remember, the goal is for students to understand what they're doing and then to be able to do it accurately and quickly. Okay, getting back to this. The way we learned to do addition when I was in first grade was with the number line. And so we had 0 in the center. And then we had 1, 2, 3, 4, 5, 6, 7, 10. And if I had to do let's say 10 minus 5, do you know how I did that? You guys, none of you learned the number line? Huh?
It's like found the 10 and then like went back 5.
I start at 0 and I draw an arrow that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the right. And so there's my 10. And then at the end of that arrow, I start another arrow that goes, because it was negative, it's going to go left, back 5. So back 1, 2, 3, 4, 5. And then for my answer, I go from where I started to where I ended, and I count. That's 1, 2, 3, 4, 5. And that's how I learned to get, 10 minus 5 is equal to 5. And that's exactly how we add vectors. We can add the vectors graphically in what we call tip to tail. So I just take my vectors. I have a 10 like this and a 5 like that. And we call the answer the resultant. The resultant is going from where I started to where I ended. And I have 5 newtons for my answer. Now, that was simple, right? Nobody here is baffled or confused by this addition, I hope. What if they hadn't been the same direction? What if I'm trying to push it forward and Casey is trying to push it sideways? And there's no friction in the tires to stop it from going sideways. In that case, we can add using the same method. In that case, we say, I have 10 newtons pushing forward, and then I have Casey with her 5 newtons going sideways. And so what's my resultant? Where's the resultant start?
At the base of the 10.
At the base where I started. And where does it end?
At the end of the 5.
At the end. And so there's my resultant. Now, is that resultant going to be 15? No. Is it going to be bigger or smaller than 10?
Bigger by like 1 or 2.
It's going to be bigger. And we could use, by now you probably know the Pythagorean theorem. We could use the Pythagorean theorem and say, 5 squared plus 10 squared, that's 25 plus 100, 125. The square root of 125, well, I know the square root of 121 is 11. So it's just a little bit bigger than 11. Yeah.
Question. So a question like this would only be a thing if there was no friction.
Yeah, I had to assume there was no friction. Otherwise, I have an additional force for friction.
Right, because you wouldn't be able to just, could you just push?
I could ask what's the net force, the total, that you and I are putting on it, regardless of friction.
Uh-huh.
But if there's friction, there would be another force to contend with. And the friction, the way it works is it would just cancel you out.
So is the reason we're doing the Pythagorean theorem because I'm pushing a different direction?
Yeah, because we made a right triangle here.
So the questions were different before because we were pushing the same direction or opposite, and this
Right.
one I'm pushing this direction?
Yep.
Okay.
Okay. Moving on. Equilibrium. Equilibrium means equal forces. I always like to point this out. We know by now, from earlier today as well as previous lectures, what is the metric unit for force? The Newton, named after Sir Isaac Newton. And what is the imperial unit, the one you're used to for force? I weigh
Pounds.
X pounds. What's the abbreviation for pounds? LBS. And what does LBS stand for? It stands for Libras.
What is it?
Libras. Like Libra, the scales of justice? Yes. Because they're the basic, Latin for force is Libra. And so that's why you have those LBS. Equilibrium is equal forces. So equilibrium very literally means you have equal forces on an object. The way we write that in physics is if you add all the forces up, they equal 0. Inside of my box, what is the first symbol? It's another Greek letter. So far, Greek letters we've used were the capital D. Oh, wow, that no one's going to recognize that. The capital D, which we call delta. Today I use the lowercase r, we call rho. This one here is another Greek letter. It's a capital S, sigma. And so sigma, capital S, is an abbreviation for sum. So we use that symbol in mathematics to mean we're adding them all together. And so where it has sigma F, that means adding all of the forces together. Another name we have, yesterday I spent a lot of time re-entering information in Quicken to get my finances back in shape because Quicken's full of fail. And in the end, I can calculate my net worth. What does it mean to calculate my net worth?
Like adding all your assets.
Adding all my assets and taking away all the debt, right? So if I have a house that's worth, let's say round numbers, $200,000, but I have a loan on that house that's $150,000, what's my net value? 50, right? Because I had positive 200, negative 150. The net is what you get when you add them all together. And so this here, if we write it out in words, we could write sum of forces, because that's exactly what the symbols mean, or I could have written the net force. And so sometimes we will write this, and sometimes we will write this. Oddly enough, your textbook drops it. I don't know if the author just thinks that writing net or sigma is too complicated for you, in which case that would be very condescending, or if he doesn't think it's important, but I think it's highly important. So this is the condition for equilibrium, that you have the sum of the forces is 0. And if the sum of the forces is 0, according to Newton's second law, we're getting ahead of ourselves, but that's in today's lecture, there will be no acceleration. So in equilibrium, the acceleration is 0. It doesn't matter if I put a vector sign over that or not, because what's the direction for 0? There is none. So it doesn't matter if I put a arrow over or not. At equilibrium, the acceleration is 0. What does it mean if the acceleration is 0 in terms of motion?
Like it's constant.
Okay, it's constant. Oftentimes we think it means it's stationary. Well, stationary is the velocity is 0, not the acceleration is 0. So something can be moving at a constant speed in the same direction, and it has an acceleration of 0 even though it's moving. So equilibrium does not mean stationary. It means that the motion's not changing. It's constant. Question?
Is it truly possible to completely be at equilibrium? Because would it, don't you think it would always be at least 0.0003 difference type thing?
No, there are some complexities to consider, like the Earth is moving and blah, blah, blah. But if we consider the Earth as perfectly stationary, when I'm in bed, sound asleep, or, let's go something that doesn't snore. If I have the stapler sitting here, it's currently in equilibrium. The net force on it is exactly 0. It's not accelerating at all.
Right.
As long as we consider the Earth to be stationary. The fact the Earth is rotating means it is changing its direction, but we have to draw the line somewhere, yeah. So yes, it is possible to be in equilibrium. So you have a problem in your homework that has a picture very similar to this picture. You have two painters, and while in this picture we have some motion, one of the painters is walking. For the actual problem, the painter is going to be at the very least at constant velocity, so it's in equilibrium. And so if it's an equilibrium, what do you know has to be true?
It's not accelerating.
It's not accelerating. The sum of the forces has to be 0. And so we look here and we say, well, what forces are acting? And I think on that problem, you're just calculating like, well, what is the problem? Has anybody done it yet? Any, overachiever?
Is that in our lab book or in the textbook?
In the textbook.
It just says like homework 01 on it?
It's on Moodle.
Well, yeah, you have to look on Moodle to actually see the assignment.
Okay.
And it has the problems actually typed in on Moodle as well. It's got to be, I know it has a figure with it, so it's either 43 or 44. I think it's 44, isn't it? Anyone? Bueller?
Say what?
The homework problem? Is it 43 or 44?
44.
Okay, 44. So 44, it's basically this picture except for the man is standing still. And it gives us numbers. It says that we have 500 newtons is the weight of this man here. And 800 newtons is the force that's being pulled up by that wire. And 400 newtons is the weight of the beam that they're walking on. 400 newtons is also the weight of the second painter. And it asks us what that force is. So based on the things I've been talking about, what principle, what idea can you use to solve this? To find that force. And this is what physics is about, is what idea is involved. I swear somebody answered, but I did not hear.
I said math.
Math. We will utilize math. Yeah, I can't list what I want to. Math. We will utilize math, but we have to have an idea first, something that we can then use to apply math. What's the idea that we will use here? We have inside that box, nothing is moving, so the acceleration is 0.
If the equilibrium means like
That it's an equilibrium. That's our idea. It's an equilibrium because the acceleration is 0. And because the acceleration is 0, it's in equilibrium, then I know an equation I can apply. And that equation is conveniently shown in the picture. The sum of the forces is 0. Now, in this case, they're all in the vertical direction, so it's easy math. We don't have to do anything hard. All I'm going to do is say, well, let's take the ones going up minus the ones going down. What's that going to equal? Okay. You are right. You did the math already. I wanted to do the math with the class here. So I'm going to take the forces up minus the forces down. Why minus? Because, of course, the direction's down. Equals 0. So I have 800 newtons plus F2, because F2 is also going up, minus 500 newtons minus 400 newtons minus 400 newtons equals 0. And I'm hoping everyone here is astute enough to right off the bat say, hey, 800 minus 400 is 0. Right? That's another, it's a quick trick we use. We don't go do any hard math with it. We recognize patterns. And then I'm going to have to add 500 to both sides. Because remember in math, what you do on one side of the equation, you must do on the other. And I'm left with F2 is equal to 500 newtons, which Eric answered right off the bat. So, yeah. Okay, so I know that's a homework problem. When you do your homework, remember, you have to show how you got there. If you just write 500 and go on to the next problem, you'll get 1 out of 10 points. Right? Because I want to see that you know how to do it. So no one will be surprised if they just write an answer and they get like 1 out of 10, even if it's the right answer, right? No matter what the question is, you have to have some reasoning, some explanation. If it involves math, you have to show the math. So I have a clear way of saying, yeah, that student, Jackie, understood what she was doing. That's the goal. Static equilibrium is stationary equilibrium. Dynamic equilibrium is equilibrium with motion. So in this case, this young lady is pushing a table, and she pushes that table and she's moving at a constant velocity, she's still at equilibrium. Now, if you were to look at the table, what forces would be acting on the table?
Friction.
Okay, there's friction. I'm going to actually do what we in physics do for every problem. I'm going to draw my table. That's my table. And now I'm going to identify them. So she's pushing it to the right. So what direction will the friction be? Okay, so I draw an arrow, and I'll put force of friction. Okay, next one. There are a lot of answers over here.
Her arms, her force. The force
Okay.
that she put.
And which direction is she pushing on it? So I'm going to put here, and I'll put this force P for pushing. I could have put FA for force applied. Nobody's going to care what you use for your symbols as long as you know what they are. What else do we have? Okay, we have the force of gravity or the weight. I make all of my forces so they start with an F so I know it's a force. Some textbooks use W for weight, which is all fine and good until you get to work. There's one more. We haven't talked about it, so I'm asking to use your experience. What?
It's the opposite of gravity.
Yeah, there's got to be something opposing gravity, because if there's nothing opposing gravity, what would happen?
Keep going.
It would fall through the floor. So the floor has to be pushing up on it to keep it from falling through. And so the normal name for it is force normal. Our textbook calls it something like the support force. I want to explain why we call it normal force, because it's going to be impossible for me to use a name besides normal force. Normal, I know, when you think of normal, you think of normal as everyday, standard, common. But normal is also a mathematical word. In math, we have words like perpendicular. What does perpendicular mean?
90 degrees.
90 degrees. Normal is a multi-dimensional version of perpendicular. So normal means 90 degrees to any line you can draw on the surface. And so if I have this tabletop, I can draw a line like this, a line like this, a line like this, a line like this. There's only one direction there are two directions actually, that are perpendicular to all of those. What are the two directions that are perpendicular to all the lines I can draw on the tabletop?
Like this.
Straight up or straight down. So those are the only two options that are perpendicular to every line I can draw on the surface. And so by definition, we define the normal direction as the direction that's coming out. So we choose one of those two. And so the normal force is the force coming out of the surface to keep something from going through it. So it'll be whatever's necessary up to the point where you break the surface. So if I push on the wall here, push it on the wall, my hand is not going through the wall, is what would happen. Because the officials didn't just, say that Tom Brady's fumble is not a fumble. Not getting angry. Since my hand is not going through the wall, what must the wall be doing?
The wall is punching you as well.
It's punching me. And what direction is that force of the wall? It's coming straight out, normal to the surface. So normal doesn't mean up, because oftentimes we think up, because like in this picture, what direction is the normal force? Up. But it's whatever direction is coming out of the surface to keep something from going into it. So those are all of the forces. Now, if it's an equilibrium, what do you know is true? It's not accelerating. Yeah. Sum of the forces equals 0. Put a vector sign on that because I have directions here to worry about. Acceleration equals 0. So now I can look at this, and we can actually take perpendicular directions. The directions have to be perpendicular to do this. But we can take perpendicular directions and treat them separately. So I'm just going to take this and say, okay, I'm going to define the horizontal direction with the symbol X, vertical direction with the symbol Y, and I'm going to say the sum of the forces in the X direction, that is the horizontal forces, has to be 0, and sum of the forces in the vertical direction has to be 0. So looking at my picture in the horizontal direction, notice there's an arrow here with my X. That means it's positive to the right because that's the way the arrow is. So the force pushing is parallel to this arrow for X. That's positive. And the force of friction is opposite, so that's negative. So the force pushing minus the force of friction has to equal 0. What does that tell you the force pushing must be? Oops, I wrote those on the wrong line. Oh, better. Got part of the equal sign. What's the force pushing going to have to be in this case? Equal to, force pushing minus force of friction is 0. So force pushing equals force of friction. And I can do the same thing for the vertical direction. I have force normal is in the same direction as Y. See the arrow for the Y? Force of gravity is opposite. So force normal must equal the force of gravity. And what's the force of gravity equal to? That's the G part, but the force of gravity had two things.
Mass times gravity.
That's right. mg. Now we don't know the mass here, so I just put it in symbols.
Equals mg. You don't have like a number?
If we had a number, if we knew the mass of the table, we know G is 9.8 meters per second squared, but we would have to know the mass of the table to put it in and get a number. And in physics, I'm very happy to have symbols for my answer. I know for most of you, you're like, no, I really, really want a number. And so, if the table was 15 kilograms, then I'd have 15 kilograms times 9.8 meters per second squared, and then I would have a number. Okay. All right. Second clicker question. A bowling ball is in equilibrium when it...
You can put anything on that.
Okay, we only have 11 people so far, 12, 13, 14. One more and we'll equal what we have for the last one. I have answers from Stacy, Eric, Haley, Skyla. Now we have 15. Carmen, Casey, Valerie, Brandon, Jackie, Vanessa, Tiffany, Hannah, Jocelyn, Larissa, Candace. What's your question, Casey?
Okay, unrelated to this question, no spoilers. So if something is like this, then the force is perpendicular are this and this, right?
Mhm.
So force normal would not be perpendicular to force of gravity, right? It would be parallel.
If you're looking at the vertical, if you have a horizontal surface,
Yes,
then force normal is going to be opposite direction of force of gravity. Yes.
right, so it would be parallel, not
Yeah.
perpendicular.
Right, they would be parallel.
Okay.
And so the force of gravity normal would be going together, but not the others. Okay, we got one more person to answer. We got 16. That's all but one. Getting better. All right, let's look at the answers. It uses white for the background for one of them. I was like, no one. 3 said at rest. 1 said move steadily. 12 said both. And 0 said none. That's a 0. So, Stacy, there. What was your answer and your reasoning?
I put C because we just talked about dynamic equilibrium because of constant velocity. So moving steadily at the same pace with
Okay. Since that one was dynamic equilibrium, what was the first one? If it's at rest, what kind of equilibrium is that? Right. Great. So it's good to have people nail the answers. So the textbook calls the normal force the support force, and this is where it's explaining it's whatever force you need to keep it from going through the surface. This is something that rings true to me. My little brother used to be very obese, and he wanted to have a bariatric surgery to help him lose weight. But in order to have the surgery, he had to know what his weight was, to qualify, and he didn't want to go to the doctor's office. And you can only buy scales that went up to 300 pounds. And so he just went to the store and bought 2 scales. And then he put 1 foot on each scale. He was at equilibrium. If he's at equilibrium, if he has 1 foot on each scale, what forces are acting on him?
Gravity and normal.
Gravity down and normal from each of the scales, right? And the scale is actually what it reads is the normal force, the force that's pushing up on you. And so if he's in equilibrium, he has the force of gravity down, which is what he wants to know. And he has the 2 upward forces. If he adds those 2 together, it'll tell him, well, sorry, I shouldn't explain it before you finished answering.
Oh, no.
He did have bariatric surgery, and he lost 200 pounds in a year. And now I'm the fat 1.5 family. Makes me a sad panda. Okay, we got 14. Should have 2 more. Two more. 15. There we go. All right, so this time we did not have complete agreement. 5902. So I started explaining, but I didn't finish. Carmen, can you finish for us?
So I chose B because if you stand on those scales, then it's not going to have your full entire weight onto the scale. So if you chose half your weight, then you can add them together and get your full weight.
Okay, perfect. Now, believe it or not, as a physics teacher, I still had to sit down and think about that when we had the real life situation. You spend so much time in the classroom. Real life, I'm like, oh, I don't know, let's think about it. You're exactly right. It has to be, if they're equal, it's going to be half your weight. Of course, you don't actually have to put your weight equal on both sides. If you go to like the county fair, you'll find lots of booths with these people from a chiropractic office who will have 2 scales set out. They'll have you step on them and they measure how much it weighs for each foot. And because we never stand perfectly symmetrically, we always lean to one side or the other. It's always going to be more on one than the other and say, oh, you have an imbalance. You need to come see the chiropractor. Well, no. You could just have been standing, There, obviously, if you have an imbalance, it would show up there, but it would also show up if you just were, like anybody else, standing not perfectly symmetrically. So don't be fooled by that. It doesn't mean you have a problem necessarily. There's a lot more that would have to be done to actually show it. So you are correct. Thank you. Okay, friction. We've talked about the force of friction, the direction of the force of friction. We all have a pretty good idea. It's whatever is opposite to the direction that it would move without the friction. So like right now, I have, let me not use, here, this is more visible. I have Brandon's backpack, and I push on Brandon's backpack. Is it moving now?
No.
So is it accelerating?
No.
And because it's not accelerating, that means it's in equilibrium. So that means the net force is 0. I'm pushing it that direction. What direction is friction going to have to point to make it not move?
Yes.
That direction. Now I make it move. I'm not going to make it move far, but while it's moving toward Brandon. What direction did friction have to move to make it stop? The opposite way. So the force of friction, whether it's sliding or not, is always going to be in the direction opposing the direction it would move without it. We actually call the force of friction two different types. One we call static friction. By now, we've seen static enough times. Static friction is the friction when things are not sliding. So ideally, when I drive my car, my tires don't slide on the road. And so I have static friction between my tires and the road. But you might say, but the car is moving, isn't it? Well, yeah, hopefully. But the rubber that's touching the road is momentarily stationary. And so the two surfaces are not sliding against each other. And so it's static friction. Now, if I peel out, because I got that kind of car. Yes, Nissan Altima totally can do that on ice. If I have my tires spinning against the road, then we have what we call kinetic friction. So kinetic friction is when you have sliding. Go ahead.
I'm sorry, how exactly, or what exactly is the definition of static?
Static friction is when the two surfaces are not moving against each other.
So they're not moving.
Right. So, for instance, let's imagine that you have a pickup truck, and in the back of the pickup, you have a box. And if you drive and that box doesn't slide in the pickup bed, even as the car is moving, the box and the bed of the pickup are stationary with respect to each other, then it's going to be a static friction between them. If you accelerate too much and the box slides, then it becomes a kinetic friction. Now, what causes friction? That's a rhetorical question here because you're not going to be able to answer. Friction is caused by the interactions between the atoms in the two surfaces. And that's kind of weird to think about because we tend to think, okay, I have the backpack and I have the tabletop, and the two are distinctly different. And the tabletop is not part of the backpack and vice versa. So the atoms are just minding their own business, but they're not really. The atoms are interacting. And so there's a certain amount of attraction between atoms in the backpack and atoms in the tabletop that makes it so it doesn't slide. There's also a certain conformity. Now, this is a nice smooth tabletop. But if the tabletop was rough, the backpack would deform so it goes up and down with the tabletop. And that would add to the static friction. Because in order to move it, you would have to bring things up. I have my fingers interlocked so that they're stuck together. And to move them, I'd have to raise my hand. And you have, even with this case, the surface on a microscopic level is not perfectly smooth. And so to get it to start moving, you actually have to lift this up a little bit. And so that makes it a little harder, so you have a little more friction when it's stationary than when it's sliding. Once it's sliding, then it's planing over. But you still have interactions between the atoms. Oh, goodness. I am the slowest lecturer. So that means you have more friction when you're not sliding than when you're sliding. Hence, when you're driving your car, if the tires are sliding on the road, you have less friction. How is this good to know? Well, let's start with the impractical. Let's say you want to drag race. If you spin your tires, you're getting less friction from the road. And it's the friction from the road that's making your car move. So when you spin your tires, you're actually going to get less force of friction accelerating you and less acceleration. So the ultimate driving would be to keep your tires from slipping, so have the maximum kinetic friction. You want to accelerate just enough so that you don't have sliding, but you're just ready to slide. If you peel out, you lose some. That's not very practical. What is practical is the reverse. When I'm driving and I want to make a turn, I don't want my tires to slide because once they slide, I have less friction, which means I have less control. And if I'm braking, I don't want my tires to slide. So we have anti-lock brakes. The idea of the anti-lock brake is you hit the brakes, most of us, we panic. We just jam down on it. And then the tires lock up, and in normal situations, you just go for a nice long slide. But you can stop quicker if the tires aren't sliding. And so the anti-lock brakes detect, oh, the tire has stopped, and it releases the brake. And so it releases the brake until the tire starts rolling again, and then it starts braking again. And so it keeps it at that maximum static friction so you can stop quicker. Also, you don't lose steering because you're having static friction for steering. Okay, I'm out of time. Well, yes, I'll go faster next week.